Please. Good afternoon. I'm Fred Gilman, Dean of the Mellon College of Science, and welcome to the second Bennett-McWilliams Lecture. First was by Alan Guth in the fall, and we hope to have this as a not biennial, but twice a year event. Fred Bennett is here, and maybe stand up a moment to be recognized. Unfortunately, Bruce McWilliams had to head out to head west and wasn't able to be here today. Our speaker today is David Spergel. He received his undergraduate degree from Princeton, then a year in Oxford, and then a PhD from Harvard. And then he went to the Institute for Advanced Study for a couple of years under the mentorship of a very good friend of mine, John Bacall. And then he moved across town to Princeton University and moved up the faculty ranks. And he's now, I love this chair, as well as, first he's chair of the Department of Astrophysical Sciences, and he also has appointments in physics and mechanical and aerospace engineering. But he's the, let's see, I'm trying to find it here. The
Charles Young Professor was started with the Class of 1897
Foundation. I love the Class of 1897 Foundation. That's such a beautiful touch. Not too many places can have a chair of that name.
Norris Russell was chair, was offered a position at Yale. Henry Norris Russell was a member of Class of 1897, and his classmates raised money for an endowment.
And the endowment is the foundation on which this chair rests. Exactly. Very good. Okay. So among David's awards is also the President's Distinguished Teaching Award at Princeton, MacArthur Fellowship, Gruber Prize, Shaw Prize in Astronomy, Helen B. Warner Prize of the American Astronomical Society. He's a member of the American Academy of Arts and Sciences, the National Academy of Sciences, and he has chaired many important panels, advisory panels, including on the National Academy's Astro 210, that's a decadal survey in astronomy. He was chair of the panel on cosmology and fundamental physics. His research interests go across a broad range. They include finding planets around other nearby stars, and then going all the way up to galaxies, galaxy formation, and of course to dark energy. He's been involved in multiple collaborations that do the observations, although nominally he's a theorist, but been very involved in the actual getting the data, gathering the data, analyzing the data, and interpreting the data. And in particular, he's on the NASA science definition team of a future space mission called WFIRST. That'll be the topic of a talk tomorrow. That's an experiment that will use a spare 2.4 meter telescope that was donated to NASA by the National Reconnaissance Office. So instead of a telescope, David's going to use it to look up. Other people used it before, or we're going to use it to look down. So in any case, this topic for today and the second Bennett-McWilliams Lecture is the observation of cosmic microwave background radiation that probed the early universe, and those measurements, which have dramatically improved over the last 2 decades. You saw it in the poster and the baby snapshots that go back to the 1990s, the 2000s, and now into this decade, that those have given us a remarkably simple interpretation of the data, and as you'll hear, in taking the universe's baby picture. David.
Hosting me here. It's been a pleasure to visit so far, and looking forward to the rest of my stay. What I want to do today is give you a sense of where we are in cosmology, focused really on the microwave background. And the microwave background's just a wonderful thing to study if you want to understand the evolution of the universe's history, because it really is, as I'll argue, the universe's baby picture. When we look at this picture of the microwave sky, and what you see here is recent data from the Planck satellite, you're looking at what the physical conditions were 13.8 billion years ago, 380,000 years after the Big Bang. And this talk, in a sense, will be divided into two halves. In the first half of the talk, we're going to start 380,000 years after the Big Bang and go forward in time and use this as the initial conditions for describing the evolution of the universe. Use this as a way of measuring the basic properties of the universe back then. Then the second half of the talk, and this is really in many ways the observational complement to Alan Gouste's talk. I hadn't realized till I got here that Alan was the previous speaker, but it works perfectly. And we'll look at how we can use these observations and other observations, and I want to say a bit about the recent results from the BICEP experiment, to look back in time, back to the universe's first moments, and actually be able to say things about what happened only 10 to the minus 36 seconds after the Big Bang. In order to have this adventure, to go back to those first moments, I'm going to have to begin by first teaching you some special relativity, and then some general relativity. But don't worry, we'll cover that in about 5 minutes. So let me begin with special relativity. The key thing to think about in special relativity for this talk is light moves at a finite speed. It takes light about a billionth of a second to get from me to you. So you don't see me as I am, but as I was a few billionths of a second ago. And those of you in the back see an earlier version than those in the front. But it doesn't matter much because I haven't changed very much in a billionth of a second. The further out we go, the further back in time we go. We go out and we look at the sun. The sun's 8 light minutes away. We see the sun as it was 8 minutes ago. When you go out and look at a nearby star, a star that's 10 light years away, it took light 10 years to get from that star to us. We see it as it was 10 years ago, and it's symmetric. If you were on a planet around a star 10 light years away, you would see all of us as we were 10 years ago, and I had more hair. Further out you go, the further back you go in time. The nearby Andromeda galaxy is about 1 million light years away. Some of the typical galaxies that are in the Sloan survey, which we'll talk about later, might be perhaps 1 billion light years away. And the further out you look in space, the further back you go in time. And that means as we look out in space at distant galaxies, we see the universe as it was. And in many ways, this makes cosmology a historical science. We look out and we watch the history of the universe. Now, we don't see the same galaxy at different points in its life. We see a nearby galaxy at recent times. We see a distant galaxy at much earlier times. And we try to tie the picture together statistically. And the thing about looking at the microwave background is we're looking out so far at the earliest light that we're seeing conditions very early on. All right, special relativity is good? Excellent. General relativity. So general relativity, as my academic great-grandfather taught me, consists of 2 ideas, as Johnny Wheeler said. Matter tells space how to curve, and the curvature of space tells matter and radiation how to move. So you can think about light traveling from a distant star to Earth, and instead of light moving on a straight line, the star is at position A. As it passes by the sun curves space, so light's deflected. And instead, we see the star not at position A, but at position B. Things get perturbed. This was Einstein's great prediction that was confirmed by the Great Eclipse Expedition. And this is a wonderful headline from the New York Times, back when it was 10 columns, so it was reliable. Lights all askew in the heaven, and this was then, so was men of science, more or less agog. I wondered what it's like to be more or less agog over results of eclipse observations. They saw what Einstein predicted. I love this. Stars, not where they seemed or were calculated to be, but nobody need worry. No more in all the world could comprehend, said Einstein, when his daring publishers accepted it. So this laid the basis to general relativity. And we've now tested general relativity in a number of different ways since then, and it's been a remarkably successful theory. Now, when you apply general relativity to the whole universe, you reach a conclusion that really disturbed Einstein, which is space is not static. He realized space must either expand or contract. And Hubble's observations showed that we live in an expanding universe. And I think conceptually, this is the most difficult thing in the talk for those of you who have not thought about it before. Because almost all of us have a Galilean, kind of a classical notion of space-time. We think of space as a grid. And I think it's easier to visualize things in 2 dimensions. So I think the picture most of us have of space is a piece of graph paper. And everything's a point on that graph paper, and the space is static. What Einstein taught us is we should think about space as something that can change with time. So let's take that sheet of paper and turn it into a ball, to a sphere. And we'll make the radius of that sphere depend upon time. So we're living on the surface of the sphere, and here are distant galaxies on the sphere. Here's us, and here's another galaxy. With time, the whole sphere expands, gets bigger and bigger. The distances between objects grow. Light gets stretched. One of the consequences of this is the universe expands, it gets colder. So if we are here, when we go back in time and look back at the distant universe, we're looking back at a universe that was denser and hotter and hotter. When we go back to the moment of the Big Bang, we're going back to a moment when the whole universe was compressed to a single point. And you can see that the Big Bang didn't happen at a particular place. It happened everywhere at the same moment in time. And another thing you should take from this picture and this metaphor is not to think of space expanding into something. Space is expanding into the future. That the radial direction is the future. And as we look to the future, we will see a universe that is bigger and bigger, denser and denser. Sorry, less and less dense, sorry. Going backwards in time. So let's just go through a quick history of the universe. The universe starts out very hot, very dense, perhaps with this period of inflation that Alan talked about. I'll talk more about later on towards the end of my talk. About 100 seconds after the Big Bang, most of the deuterium and helium in the universe formed. About 500,000 years, to be more precise, about 380,000 years after the Big Bang, electrons and protons combined together to form the first atoms. About 100 million years after the Big Bang, stars really started to come into their own. And galaxies like our own started to assemble around 1 billion years after the Big Bang. And we live here today about 13.8 billion years after the Big Bang. To put some numbers in perspective, our solar system is about 4.5 billion years old. So that's an interesting number. It's comparable to the age of the universe. It's about a third of the age of the universe. It's small. We've only been around our solar system for the last third, but it's comparable to the age of the universe. One of the key parts of this cosmological picture is the existence of this cosmic microwave background radiation. The cosmic microwave background radiation is the leftover heat from the Big Bang. You should think of the universe starting out very, very hot and very, very dense. And as it expands, it cools. When atoms form here, it becomes transparent, and light can move freely from then to now. So what the microwave background mostly reflects is physical conditions back 380,000 years after the Big Bang. When we look out at the microwave background, this is what we see. It's almost the exact same temperature there as is there and there. It's nearly uniform radiation, about 3 degrees above absolute zero. It's first seen by Penzias and Wilson at Bell Labs when they were looking around at the microwave sky. Those of you who are old enough to have watched television, not with cable, but with an antenna on your roof, have seen the microwave background radiation, because when you tune your TV between channels, about 2% of the static you see is microwave background radiation. And those of you who are younger have merely just heard it, because when you tune your radio between stations, about a couple percent of the static you hear is actually this radiation, the microwave background radiation. And you can take your a telescope on your roof and go see this uniform component. If you look more carefully and make a more sensitive experiment, at the level of a part in 1,000, you'll notice that it's a little bit hotter on one part of the sky, a little bit colder in another, and that variation in temperature is due to our motion. And when you look with even more sensitivity, and these are the fluctuations first seen by the COBE experiment, there are tiny variations at the level of about a part in 100,000, temperature variations of about the level of 10 Kelvin. What you're looking at in these pictures are maps of the sky. We're basically taking the sky, which is a sphere around us, and showing it much like we'd show a map of the Earth, where here's the South Pole and the North Pole and the equator. In this picture, we're doing this picture in galactic coordinates. This is the galactic equator. This is the disk of our galaxy. The disk of our galaxy has lots of hot gas. It has relativistic cosmic rays. It has lots of warm dust. And you're seeing in these pictures emission from dust and electrons moving in the magnetic field of our own galaxy. And to get to something I'll come back to at the end, one of the challenges in studying the microwave background is separating out this cosmological signal from this signal from our own galaxy. This is stuff that has been traveling to us for 13.8 billion years, and this is stuff that's nearby stuff. It's been traveling to us for a few thousand years. My own involvement with microwave background experiment began with my work with the Wilkinson microwave anisotropy probe. Here's my late colleague Dave Wilkinson, who played a key role in the COBE experiment and helped get WMAP started. And it went out, and I'll show some data first from WMAP, and then more recent data from the Planck experiment. WMAP launched over 13 years ago. It's actually now turned off. Planck launched about 4 years ago, and so a European-led experiment in which there's a significant US contribution. With all these experiments, as I've mentioned already, we're looking back in time, looking back to when the universe made the transition from being ionized to being neutral, and making a snapshot of what the universe looked like then. Well, I showed you the pictures from COBE of the microwave sky. Here's the pictures from WMAP. This is a next generation after COBE. It's higher resolution. And you can see, again, emission from the galaxy. And then here's the cosmological signal. Now, the key way we can distinguish between galactic emission and the cosmological emission is its dependence on frequency. These are measurements at 22 gigahertz. As I go up in frequency, the emission from the galaxy starts to drop in this range. The galaxy gets dimmer at higher frequency, and dimmer, and dimmer. And if you start looking at the patterns here, you see the patterns look the same at different frequencies. And that's one of the ways we can separate out these galactic foregrounds and focus on the cosmological signal. And we can separate them all as best we can, and this represents a relatively clean map of the sky around us, where we've done the best we could at the time to remove the galaxy, some tiny residual emission here, but this represents a pretty good overall picture of what the universe around us looked like 13.8 billion years ago. And what we like to do is look at this pattern and study the lumpiness as a function of scale. What is the characteristic scale of the hot and cold spots on this map? Turns out there's about 40,000 1-degree scale spots here. There's some features that are bigger. What we'll do is statistically characterize that. And we look for unusual anomalies. My favorite anomaly is the letters SH that appear quite clearly here. I first saw these when I was sitting at the Davis Cosmology meeting in 2003, and Stephen Hawking was giving a talk. And he had our data behind him. And I assumed this was a joke put by one of his students when the SH appeared, but I opened up my laptop and looked at our data, and there it is. It was 2003, it was the time as we were gearing up for the Iraq War. I used to claim that this was a message about Saddam Hussein. Now, I like to think that we are missing 2 letters here, and it was an early message about some mistake made when our current version of the universe was created. But besides looking for letters, what we like to do is look to measure how lumpy things are as a function of scale. What we measure is what's called the galaxy angular power spectrum. And this is just a statistical measurement of the lumpiness of the universe, the characteristic temperature fluctuations, versus scale. And the units we use are called multipole moments, but they're really just measures of 180 degrees over angle. And you can see there's a characteristic scale for the lumpiness. That characteristic scale is about a degree. This degree scale is set by the physics 380,000 years after the Big Bang. If you set up some variation in density from place to place, you create a region of excess pressure. We'll do this experiment right now, reproducing what happened right after the Big Bang. We'll create a region of excess pressure. What happens? It produces a sound wave. The sound wave travels outward at the speed of sound. In 380,000 years, it travels about 380,000 light years in radius. So that sets a characteristic size for the hot and cold spots. Now I get to do some geometry. I measure a distance. I have an angle that tells me how far the light has traveled. From that, you can see that, assuming space is flat, that light's been traveling for about 13.7, 13.8 billion years. So that gives us a direct geometric measurement of the age of the universe. We can also infer from this its composition. The way those sound waves propagate depends on the property of air. If I was generating those sound waves by striking a piece of metal, the sound wave travels at a different speed. So I can measure the composition of the universe, measuring how many atoms there are by looking at the speed of sound. How the wave evolves, its own self-gravity depends on the density of matter. So I can measure the basic cosmological parameters. And what is remarkable is with really 6 basic numbers, the density of atoms, the density of matter, the age of the universe, how lumpy the universe is, and how that lumpiness varies with scale. And then another parameter, because star formation scatters light way after it ionizes, I need to know when the first stars formed. But with those 6 numbers, I could completely fit the data we have here. And these 6 numbers, turns out our universe is remarkably simple, completely characterizes the basic properties of the universe. So I like to think about that as we've taken the universe's baby picture. And these show pictures of 3 randomly selected babies 3 days after they were born. And then we can evolve them forward in time to the summer. And given the initial conditions, you can extrapolate forward to today. Now, this does not work that well with babies. At least that's not been my experience. It's difficult to predict from these initial conditions what happens then. But the universe turns out to be much simpler. We can start with a computer simulation of the initial conditions, evolve them forward in time, watch the structure form, and based on the statistical properties of the initial conditions that we see today, we can run them forward in time and predict how lumpy things should be today and compare our observations to the theory. And they do remarkably well. And one of the great successes of the theory is this comparison. And this plot in the upper right-hand corner shows a measurement of the lumpiness versus scale, where the blue curve is the best fit model to the microwave background, no free parameters. We then compare it to the galaxy observations today, lumpiness versus scale. And you can see it's a beautiful fit. And you'll notice there's this waviness in the curve. We can then look at the waviness, and this is work done and led largely by Shirley Ho here, using the Sloan Digital Sky Survey. This is some results that just came out this year. You saw those sound waves, that pattern of fluctuations we saw in the microwave sky. Those same sound waves produce a signature in the large-scale distribution of galaxies. And here are these sound waves in our universe nearby. And this curve is based on the fit to the microwave background. And it very nicely fits the galaxy model. So we have this simple model that all seems to fit. General relativity, a uniform universe giving us the Big Bang, a universe that's flat, strange universe. Atoms make up only 4%. We don't know what makes up 96% of the universe. But it does all seem to fit together. I don't have the time to go into all these different ways we have of testing the properties of the universe, looking at distances from supernova, measuring the Hubble constant, measuring the age of stars, properties of clusters, gravitational lensing, absorption line statistics. Rupert and Rachel is a number of experts on various parts of this story here. But broadly, they all fit together. We have this coherent cosmology. This is something, to me, that is quite remarkable. When I started out in this field 3 decades ago, this is not what it looked like when I was an undergraduate. Right? We did not have a simple model where we measured all the parameters well, and it all fit. And broadly speaking, it all fits together. So when you have a model like this, you want to keep pushing and seeing what happens as the data improves. And was going to go push to smaller and smaller scales. And I'll talk next about observations first on the ground at small parts of the sky, and then look at observations from Planck. And what's nice here is you have models that make predictions. This was the WMAP data after 9 years of observation, and it very nicely saw these 3 peaks from the sound waves. But the model predicts there should be more that we should see on smaller scales. And what's been going on, in complement to the work in space, is work both from balloons and from the ground. Most of the work on the ground is happening at 2 places that in some ways represent about as close as we can get to space and still be on the ground. One at the South Pole, where at the South Pole station, there's been a whole series of experiments, and I'll talk about it towards the end of my talk about some recent results from BICEP. Now, when we talk about high-resolution experiments, I'll focus on some numbers from the South Pole telescope, a big telescope here at the pole, led by John Karlstrom, and some results from the Atacama, a high and dry point up in Chile, right near the border between Chile and Bolivia, in this high, dry desert. Another very good place to operate a telescope like this, and you want to get away from the humidity. And here's a picture of this telescope. If you have a telescope pointing up, one of the nice ways to get a good picture is you go to Google Earth, you type in the coordinates, and there it is. On these telescopes that Fred mentioned, if you go to Google Earth and look at your house, you'll notice things like they can count from that satellite, the properties of you can look at my roof and see how many windows we have in my roof from Google Earth. That's a much smaller satellite than we got for this telescope. So the ones that are looking down, they're good. They can see a lot. So what do we do with these telescopes on ground? One of the things we do is we zoom in on small patches and look at them at much higher resolution. So this is the WMAP map, and you can see we took a little patch and zoomed in on it. Didn't map the whole region that we saw from space, but we got high resolution data. And this shows the results as of last year, measurements from Acton SPT pole. And here's our theory. This is before we include the effects of gravitational lensing. And the theory and the data agree very nicely. We go, these data improves, it still fits the model. What generated a lot of excitement last year was the first set of results came out from the Planck experiment. Planck has surveyed the sky 5 times. Last year, in March, they released the results of 2 surveys of the sky. So they mapped the sky twice. What they will do this December, and I'll get to this at the very end of my talk, is they'll release the results of 5 surveys of the sky. And they've made measurements both of temperature fluctuations and fluctuations in polarization. And up to now, they've only released in detail their temperature maps, but they've shown us pictures of their polarization maps, something I'll get to towards the end. So first thing you should take away from the Planck measurements is it's a remarkably consistent picture. This shows on the top the WMAP data and the Planck data at the same resolution. And I challenge you to find significant differences by eye. It agrees at this level really well. And Planck has provided an even more complete picture. With WMAP, you saw the 5 low-frequency maps going up to about 100 gigahertz. Planck went to much higher frequencies, which gives us not only more information about the microwave background, but more information about the galaxy and galactic dust. And while the WMAP and Planck data clearly agree very well on the resolution of the screen, Planck has additional information on smaller scales that you have to kind of zoom in, as is shown here, to see what's there. And again, to give you a sense of the broad consistency, this compares at roughly the same frequency what we measured from ACT on the ground and what Planck measured in space. And it's very reassuring when completely independent experiments using very different techniques see the same thing. And, you know, we see a very consistent cosmology. I'm showing the measurements from ACT and SPT and WMAP and flashing back and forth with Planck. And the overall picture you should take away is remarkable consistency. Though as someone who works on this, I look at this and I say, around here it doesn't quite agree. These points are a bit off. And this whole region here is a bit low. So I'll spend 5 minutes on a detour worrying about those differences, what I did this summer, past summer, because you look at these basic parameters, how the fluctuations varied with scale, how much matter there is, how many atoms there are, how fast the universe expands. For the graduate students in the audience, this is what I always tell my students never to do, which is put up charts of numbers. But in this case, I think it's actually useful to stare at them and say, let me look at something fundamental like the expansion rate. And you can see within the errors, this is Planck and this is our WMAP and ACT numbers, these look basically consistent. And you'd say these two experiments agree, and that's mostly right. Except these two experiments looked at the same universe. These errors are correlated, and the values should actually be closer given they looked at the same universe. Another hint that there might be something awry comes from measurements of the lumpiness of the universe versus scale. The red curve here shows the best fit measurements of the amplitude of fluctuations and the density of matter based on observations of the microwave background. The blue curve shows the Planck team's best inference based on observations of clusters of galaxies. Now, when you look at this plot, you say, these two don't really agree. That means there's one of three things going on. This data is wrong, this data and analysis is wrong, or the most interesting possibility is the model I used to compare the two is not correct. And that would be the most interesting outcome. I'm going to focus on the problems with this in the next 5 minutes. But you can ask Heat Track or Nick Battaglia here about some of the problems with this curve. And Nick and he will tell you that it probably should be shifted up a bit, though I won't have time to get into that. I'll focus on some work actually done with someone else who will be here soon, Raphael Flauger, who's a postdoc at the Institute, Renee Lozek, who's a postdoc at Princeton, where we took the publicly available Planck data. One of the wonderful things I think we all now do, or try to do in cosmology, is we make all of our data eventually publicly available. That means other people can test it. And they made their data available, made their basic codes available. So we checked some things. So one of the things I found was that a lot of the problems came from one particular Planck channel, 217 gigahertz. Remember, they mapped the sky at 9 frequencies. We took the Planck 217 gigahertz data, looked at, this is the best fit parameters that come from the Planck analysis, take the Planck code. We then took their code, and we just said, let's zero out the weights of the 217 data, and then draw from that various realizations of the universe, assuming the noise that they say is in the 217 data. And this is what you should find. This is from 500 realizations. Not one of them had the parameters, and this is the the expansion rate of the universe, the density of matter, lumpiness, the scale dependence of the lumpiness. Not one of them had this big a shift. Now, these are small changes, right? We're talking about differences in the Hubble constant of about 1 kilometer per second per megaparsec. When I was a graduate student, people would go to meetings and argue whether the Hubble constant was 40 or 100. And that was kind of the low and high range. Today we're arguing, is it 67 or maybe 71? So there's still a high and low camp, but we're a lot closer together. And so these are small differences. And you can see this in the parameters. This is what comes from the official Planck numbers. This is our WMAP plus ACT numbers. This is what happens if you throw out the 217 channel. It has remarkably good agreement with the pre-Planck data, albeit with somewhat smaller error bars. And when you do that, a bunch of things go into better agreement. This is a summary of where things are with clusters. We go from this blue curve to this purple curve. It's a modest shift, but at the same time, if you reanalyze the clusters, and that's this gray band here, Nick Battaglia is part of this analysis here, you can see now everything seems to fit together. And it seems to be that we just needed to refine the analysis. We actually think we've identified, and I think the Planck team has agreed with us, the source of the problem, which is in the Planck 217 data during the first month of operation. The detectors were all sitting in a cooler that was vibrating, producing common mode noise. And if you analyze the data where you cross-correlate two detectors that have common noise, that gives you an erroneous signal. If you take the Planck data, remember they have 2 seasons of data, only cross-correlate season 1 and 217 with season 2, that gives you something completely consistent with all the other things we've done. So we think we have isolated the source of the problem. It's a subtle one, but it does affect the cosmology. So in the last 15 minutes, let me now go back in time and use the microwave background to tell us about the early universe. And in order to do that, I need to introduce this idea that Alan Guth talked about in this previous lecture in this series, the idea of inflation. And the way I think about the motivation for inflation comes from having taught for a number of years. If you give an exam, and every student in the exam room hands back the same solution, one of 2 things has happened. There's either been communication in the room, or everyone shared the same information beforehand. The same thing is true of our visible universe. When we look at our visible universe, we look, say, at that microwave sky, we're looking at many different patches on the sky. This region here, and this region here, and this region here, and this region here, in the standard Big Bang theory, have not had any time to communicate with the other region. They've not been in causal contact. Yet, to 1 part in 100,000, they handed in the same answer. They have the same temperature. So that requires either some way of having them to communicate with each other, or some special initial condition where they all shared some common information. But you need not only to have things close to identical, they can't be exactly the same. Every student has to differ from every other one by about a part in 10 to the 4. You need some source of fluctuations that have these right properties. Otherwise, without fluctuations, a perfectly smooth universe would stay smooth forever. We also have to understand why the geometry of the universe is so close to flat. We find a universe whose kinetic energy, the energy of expansion, exactly balances its own self-gravity. This is a lot like finding a pencil balanced on a point. It's an unstable configuration. And this fact that the universe is so big, it's so old, it's so close to this not unstable fixed point tells us that there's got to be something wrong with our basic assumptions. And what we think it is the idea that the universe underwent what's called a phase transition, something like inflation during its early history. It was in a state of what we call a false vacuum. It's a lot like having supercooled water that you just add a tiny perturbation will become ice. And in this false vacuum state, this energy associated with it drove an enormous expansion. And during the first moments of the universe grew by factors of 10 to the 60 to grow from a tiny little volume to be the whole visible universe we see today. In doing so, and growing from a tiny region to a huge volume, it got stretched and became flat. And this inflationary theory turns out to make a whole series of predictions about the properties of the universe. During this period of expansion, tiny quantum mechanical fluctuations in the density of the universe field will grow to form fluctuations that can grow to form galaxies, the stuff we see in the microwave background, and ourselves. These tiny quantum effects can also produce fluctuations in the gravitational field that will produce a background of gravitational waves. And if I had another hour, I would go through the basic inflationary predictions that were all made in the 1980s of a universe that was close to flat, had fluctuations that were nearly the same at all scales, fluctuations that are described as being Gaussian, what we call adiabatic. By that I mean the same ratio of electrons to photons in that part of the universe is the same as that part. Fluctuations existed on scales that were never in causal contact. And one of the things we showed with the WMAP data, been measured to higher precision with the Planck data, is we checked off these 5 tests, confirmed inflation. If I was giving you this talk a month and a half, 2 months ago, I would say the last great prediction is gravitational waves. And the way we will look for them is studying the polarization of the microwave background. When we look at microwave background photons, we're seeing photons that interact with electrons. And in doing so, these scattering produces a polarized signal. You can think of it happening this way. If I'm an electron, if a photon comes in this way, it's going to scatter to you with a polarization, an electric field pointing that way. If a photon comes in this way, scatters off my nose, it'll come with this polarization. So if I have more photons coming in from the top than from the side, I'll see more photons with this polarization than that polarization. So you can see how that pattern works. If I have a pattern of hot and cold spots, these photons will come in this way and scatter to you with this polarization. Well, here you'll get that polarization. So there'll be a correlation between hot spots, cold spots, and the polarization pattern. And we've seen this temperature polarization form. If we zoom in on this region here, you can see that it has this very regular pattern, a pattern of polarization that we call E-like. And this has the property that if I take this picture, or this one, reflect it in a mirror, it looks the same. It's symmetric under mirror reflection. The other possible pattern is what I call a B-like pattern, one that's anti-symmetric under mirror reflection. Gravitational waves, which are predicted in this inflationary theory, predicts equal numbers of E modes and B modes. And what's been created a great deal of excitement in the field is some recent results from the BICEP experiment here at the South Pole, doing some really heroic science in that they're doing very sensitive measurements in difficult conditions. They've built these array of experiments. And, I was talking about measuring temperature fluctuations with Kobe and WMAP and Planck, and those fluctuations were a whopping 1/100,000th of a degree, 10 microkelvin. The polarization fluctuations, that E-like pattern, those are typically a microkelvin. The temperature fluctuations get up to 100 microkelvin. So these E-like polarization patterns are 100 times weaker. But the gravitational waves they're looking at are even weaker than that. They're 1/10 of a microkelvin, 100 nanokelvin. So they're really tiny, sensitive fluctuations. And what really has created tremendous excitement for many of us in the field is the announcement by the BICEP team that they've detected this pattern of fluctuations. And what's shown here in red is what we expect just due to ordinary fluctuations in the effect of propagation through space. But they saw this excess signal in the BICEP experiment that looks very much to be consistent with the predictions of inflation. Not only that, if this is right, we're seeing quantum fluctuations in the gravitational field, actual gravitons, produced in the first 10 to the minus 36 seconds of the universe. We're telling us a lot, given just the measurement of this amplitude, tells us a lot about the physics of inflation and has profound implications for fundamental physics and cosmology. Well, there's been a lot of excitement about this result. My reaction to it, this may be being a bit of an old cynic, is that important results deserve careful scrutiny. And I get nervous when results come out that don't have the paper on systematics and doesn't tell you what journal it's been submitted to, but has a huge press conference, and a lot of the details are missing. So we've been trying to look into this in detail, and the last 5 minutes is very much kind of my own work in progress with a number of colleagues trying to understand, is this signal on the sky? Is this signal cosmological? The one that worries me the most is this question here, because you saw that we always have to worry about the galaxy. And this figure here comes from the Planck team. So the Planck team has not published their polarization data, but they've actually given conference talks, which they've posted on the web, showing their polarization maps. And what they see is consistent with what we saw on small patches from other experiments or at lower frequencies from WMAP, but we have higher precision measurements of the properties of these galactic foregrounds. And the galactic foreground that worries me most for this experiment is galactic dust. Now, they've looked at a very low dust region, but the problem is it's a very weak signal. It's 0.1 microkelvin. And remember when we looked at the WMAP and Planck data, WMAP had 5 frequencies, Planck had 9 frequencies. If you want to be sure that the signal is cosmological, you want to see the same thing in all those frequencies. And pretty much the BICEP experiment has effectively one frequency. They have a little data at the second. But with just one frequency, you have to rely on your models from other regions. And what they did, and this is from their paper, is they took the figures you saw from those papers. They made an estimate, and this is probably the most complete estimate right here, of what the foreground signal should be based on measuring the polarization off the data. And what worries me is that when they did this, they ignored the contribution in the Planck measurements from distant galaxies, what we call the cosmic infrared background. When you measure the polarization signal It's the sum of the signal from our galaxy and distant galaxies. The intensity signal is a signal from our galaxy and distant galaxies. And those two are roughly comparable, our galaxy. The distant galaxies, as we see lots of them, aren't polarized. So if you characterize the overall polarization by the ratio, you need to correct for this fact. And that's about a factor 2 to 3 correction in polarization amplitude. And since you measure power, you've got to multiply by that squared. So you've got to take this dashed blue curve, which is their estimate of the galactic contribution, and multiply it by a factor of 4 to 10. That suggests that the galactic foreground could be their entire signal. This is something I've talked to members of the BICEP team about in the last week, including their PI on Friday. They've now agreed they need to recheck this, and I've been told they're redoing their estimates here. So we will see. But most importantly, it could turn, I think, I'm not contending we know this is galactic. I just think with one frequency, we don't know it's cosmological. And I think this is one of an example of what is the way we ought to be doing science, which is these guys are going after a very important question. Can we see the first moments of the universe by looking at gravitational waves? And they're doing this by building really sensitive experiments that go to, that really push the forefront of the field. And when you have an important result, what we need to do is test it. And we're in the fortunate situation that within the next 2 years, I counted 7 experiments that will test this result independently. And this is going to be great, because we'll either have this result confirmed, which will be wonderful, or we'll learn that there's problems here. The Planck experiment, as I've mentioned, has polarization data. They are going to release the polarization data in December. These are all challenging measurements, so they're working hard on calibrating it. The SPT experiment has already gotten data on the same region of the sky, and they're analyzing it now, and they will be able to confirm that it's on the sky. Because it's at the same frequency, that won't be enough to know that it's cosmological. This is the polar bear experiment, which will also look at the same region of the sky. This is the ABS experiment, is right there. That will look at it. Here's ACPOL, which will look at that same region of the sky. This, to me, is the most tragic picture in some ways, though I hope it'll work out okay. This is the SPIDER experiment. It's a balloon experiment that was supposed to have flown last winter. Its multi-frequency would actually have, I think perhaps of these, the most sensitive measurements in the next year or so. They were all set to go. They were at the pole, ready to fly. And then sequestration hit. And the NSF told them that they had to withdraw all their people, and they canceled the flight. And the way the scheduling works at the pole, you lose that launch window of just lose a month, that's it. And the people I feel worst for are these guys, who are the graduate students working on the project who thought they were graduating this year. And those of you who were enthusiastic supporters of the Tea Party sequestration moves, think of them the next time you decide to sequester the budget. And this is an EBEX experiment, which flew this past winter, had some technical problems. So my understanding is the data is not good enough from the current flight, but they'll be flying again. And there are several other experiments that are either underway or being constructed that will also weigh in. And we'll know what's going on. And not only that, if this turns out to be right, we'll start to characterize this gravitational wave background to higher and higher precision and have a window into the first moments of the Big Bang. So the story that I've told about the temperature fluctuations in a way, is just the beginning. You've seen we've learned a lot from measuring those, and we're about to learn, I hope, more through measurements of the gravitational waves in the first moments of the Big Bang. So let me stop there. Thanks. Sure, questions?
Is there a mic, or should I just shout?
Just shout, I'll repeat the
Okay.
question.
You said that what worried you most was the cosmic infrared background.
Right.
About the bicep results. There's been a paper recently in the archive that one of the faint galactic loops
Yes.
overlaps the bicep
Yes.
field. Could you comment on that?
That's the thing that worries me the second the most. So there are two sources of foreground emission that are important. Let me go back just to show what the sky looks like as a, there we go. So this is the Planck results, the function of frequency. This is galactic dust, which is dominant at high frequencies and becomes less important as you move down in frequency. And then in that plot, dominating at 30 gigahertz, is the synchrotron emission. And you can actually see here, see this loop here? That's a radial loop. That is the boundary of a shell of a shock generated by a supernova, or actually probably a series of supernovae. And these big shells are where cosmic rays are accelerated. And it turns out that one of these shells passes right through the bicep region. And if you take measurements not from Planck, because we don't have the polarization measurements yet, but from WMAP at 22 gigahertz, and extrapolate to the bicep frequencies, the bicep team concluded that the fluctuations would be a trivial contribution. In doing that extrapolation, they assumed a slope that, was optimistic for them. They assumed a slope of minus 3.3, and that's, I think, there's really no reason. The data suggests closer to minus 3. Doesn't sound like a big difference. When you extrapolate over that range, it adds up. If you take that minus 3 value, you'll get a contribution from the synchrotron emission that's at most about 15–20% of the signal. But, so there's a paper actually by Vehus and a couple people on the web that came out yesterday about that. But I think things could be worse because of these shells. Because we know that cosmic rays are accelerated at that shock. So I need to draw, if you've got, at low frequencies, you may be dominated by the typical galactic region. As we move up in frequency, you might start to have a change in slope because you start seeing the young cosmic rays. And if that's going to happen somewhere, it'll happen here. So there's a possibility that synchrotron could be more significant. And the two add together because we're measuring the square of a signal. So if synchrotron was 20% of the variance, that would mean that it's roughly a third of the signal or so. And then if the dust was 2/3, it's trouble. That's the worst case, that it's all galactic. It could be cosmological, but my feeling is that based on having one frequency of data and what we know about the galaxy, we can't be confident. And I think their paper did not properly evaluate the galactic foregrounds. They didn't know about this loop.
Another question?
Yeah.
Just a stupid question. What is the sigma A limit across mean?
Sigma h, just some notation we use to measure the lumpiness of the universe today. Technically what it is you take a sphere that's 8 megaparsecs in radius and throw that sphere down in a random place in the universe and ask, what is the variance on that scale compared to the mean? How lumpy the universe is. It turns out that there are order unity, actually about 0.80, 0.81 fluctuations on that scale. That's today about the scale that characterizes the lumpiness of the universe. It's the scale if you look at galaxy clustering and ask on what scale, if you look at the galaxy correlation function, what scale is it about 1 that you find extra stuff around you? It's about that 8 megaparsec scale. That's why we use it. It's also the scale of clusters. If you look at a massive cluster and ask, if I assemble material on this scale, I will get among the largest objects we see in the nearby universe. So it's a useful scale to calibrate things and represents about the transition between the linear regime and the nonlinear regime. And since we want to compare the lumpiness of the universe at redshift of 1100 with the lumpiness today, we want to choose a scale to make the comparison on. And it's just like all fields, you have standard notation. And this is the standard notation we use. And to make things even slightly more confusing, it's not really 8 megaparsecs. It's 8 megaparsecs divided by the Hubble constant in units of 100 kilometers a second per megaparsec. So sigma 8 is actually the variance smoothed on the scale of about 12 megaparsecs. So, this is the nature of historical notation.
One more question? No? Thanks, David, again.